Okay, so this Runge-Kutta method has a absolute error of big O of h to the fifth. So as h gets smaller and smaller, this is going to become very a small absolute error, and so that's going to be great. It's going to give us a much better approximation than Euler's method or modified Euler's method or any of the other Runge-Kutta methods of order 2. Okay. Are there Runge-Kutta methods of order 3? Yes, but nobody talks about them. They're not very useful. So Runge-Kutta method of order 4 and a Runge-Kutta method of order 2 are used a lot, right? Modified Euler's method. Okay. So let's look at an example. Of course, it's going to be with our favorite differential equation. Use Runge-Kutta method of order 4 with h equal to 0.2 to approximate y of 0.2 for, we have y prime equal to y minus t squared plus 1. Y of 0 is equal to 0.5. Again, we have our differential equation. We have y sub n plus 1 equal y sub n plus 1/6 of all those guys, k1 plus 2k2 plus 2k3 plus k4. Okay, I'm not going to go through and write all those things down again. I just want to write that part where we have y0 is equal to 0.5. That's our initial value of our differential equation. So we have n, t sub n, y sub n. I don't even need to have this table be very big because we're only going to compute one value. 0 and 1, this is 0, 0.5, 0.2 is what we're going to use here. Okay, and at t equal to 0, my function is 0.5. So let's plug it in and see what we get. K1 is equal to, let's go with it here. We know that's just going to be f of 0, comma 0.5 times h, which is 0.2. You guys remember this is going to be, if we do this, actually we haven't done this one before, with 0.2. So this is going to be y is 0.5 minus 0 squared plus 1 times 0.2. So I get 1.5 times 0.2, have 0.3. What I have here. Right, because it's 0.2 is 1/5, yes. Sorry, K2 is going to be, if we look at this, it's going to be f of t0 plus h divided by 2, so it's going to be 0.2 divided by 2, comma. Let's put in what t0 is. Just we know it's going to be t0, so t0 is 0. Okay. Comma y sub 0. Y sub 0. Y sub 0 is 0.5 plus K1. K1 is 0.3 divided by 2. All that times h, 0.2. So let's simplify this a little bit. So we get f of, I think that's what, 0.1, comma 0.65 times 0.2. Oh, a lot of work there. And if we plug that in, so we get, this is my t, this is my y, right? So I get, in this case, 0.65 using my differential equation minus 0.1 squared plus 1 times 0.2. And when I plug it in, I get 0.328. So that's my K2. Let's just box these guys so we know what we have here. Okay. K3 is equal to F of T0, right? We're still dealing with our first iteration, T0, which is going to be 0, plus H, which is still 0.2, divided by 2, comma, Y0, which is still 0.5, plus K2. K2 is 0.328 divided by 2 times H. So we get F of 0.1. This is 0.614, I think. 614 times 0.2. Check that. 0.664. 664. Okay. 0.664. So that when we plug that in, that is, my T is 0.1, my Y is 0.664. So when I plug in, I get 0.664 minus 0.1 squared plus 1 times 0.2. When I do that one, I get 0.3308. 3308. Okay. K4 equal to, so our last one, F of T0, which is still 0, plus H, so 0.2, the whole thing, comma, Y0, which is 0.5, plus K3, which is 0.3308. Okay, so that becomes F of 0.2, comma, 0.8308. 8308. And what happens when we do this one? Plug this one in, get 0. So my T is 0.2, my Y is 0.8308, so I get 0.8308 minus 0.2 squared plus 1 times 0.2. Oh, I forgot my H. Thank you. That's right. So this K4 is going to be this times 0.2. So this should be at times 0.2 as well. Sorry about that. And when you work that out, I have this is equal to 0.35816. Double check that real quick. And my calculator here. So many numbers being thrown around, it's always a good idea to check it again. All right, so that's what I have, 0.35816. Hopefully the other ones are good. Okay. Now, we did all of that so that we can predict Y1. We haven't predicted Y1 yet. So let's do that next. y1 is equal to y0 plus, so well, we know what y0 is. Y0 is 0.5 plus 1/6, right, of k1, which is 0.3, plus 2 times k2, which is 0.328, plus 2 times k3, 0.3308, plus k4, 0.35816. Oh goodness. This is equal to, if I did this correctly, I have 0.8292933. That's what I have. 0.8292933. The actual solution, I think we said this last time, at y of 0.2 is 0.8292986. So we actually got up to the first 4 digits. 1, 2, 5 digits correct, right? 1, 2, 3, 4, 5 digits correct in our approximation using one iteration. But look how long it took us just to do one iteration, right? With Euler's method, you would have been able to do like 5 or 6 iterations in the same time span. But of course, we would have had to make h much smaller to get as good an approximation as we're getting here now, right? So here, what we have to make sure to know is that although Runge-Kutta method requires 4 function evaluations, right? We have to do K1, K2, K3, K4. Euler's method only requires 1 function evaluation per step, but the accuracy of Runge-Kutta far outweighs how many function evaluations we have to do. So that's why Runge-Kutta is superior. Although we are doing 4 function evaluations for each of this, for h equals 0.2, to get the same accuracy with Euler's method, we're going to have to do many more function evaluations than this. I know that per step, Runge-Kutta method only uses 1 function evaluation. But to get this accuracy at 0.2, you might have to make h equal to like 0.001, right? And to get this amount of accuracy. So that means you would have to do essentially 200 function evaluations to get to y equals 0.2 and get this amount of accuracy in your approximation. Anyway, hopefully that makes a little bit of sense why Runge-Kutta method is far superior. Although it seems like you're doing a lot more function evaluations, and you are per step. You are doing a lot more function evaluations. In general, you don't have to use as small an h value, which makes it a superior method to use. All right, so that's it for this particular lesson. We're not going to do any more in Runge-Kutta. We're done. And we'll see if we do any more things after this. All right, talk to you guys later. Bye.